Good morning. Today we will be continuing with the examples for compound propositions. So we have seen an example in the earlier class. Let's continue with another one. So this is the next example. I have already created the columns for the truth table and also filled the P and Q values which are common. One thing that you're supposed to remember over here is that if you have two variables, you will have 2 square, that is 4 rows. So this power indicates the number of variables. Okay, I've already taught this, but let's just remember this point that if you have two variables, you will have 4 rows, and if you have 3 variables, you will have 8 rows. So in the earlier example, we have seen it with 3 variables. Now we just have only 2. Now we have to first find the negation of Q. The negation of Q will be false, true, false, true. Now, after that, the next thing is by implication or by conditional. For by implication or by conditional, the rule is the biconditional is true when P and Q have the same truth values. So over here we have to look for these two columns, and the biconditional is true when they have the same values. So P is true, Q is true. So we will put it true over here. And P is true, Q is false. So we write false. Similarly, false. And since both of them are false, this will be true. Now we have to OR both of these rows. Okay. So the rule for OR is that if one of them is true, then it will be true. So if one of them is true, this is true. So the rule is true. Similarly, negation Q is true, so true. Both of them are false, so false. Both of them are true, so it is true. Okay. Next. Similarly, we have another example, and this one is quite simple. Please try to solve it. And this is directly P or Q. So P or Q is one of them being true. We have just seen that. So true, 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 false. The next one is P and Q. And is if both of them are true, then only true, otherwise false. So true, false, false, false. Now, for exclusive OR, if you remember, that is the opposite case of biconditional. That is, the rule is when exactly one of them is true, it is true. So over here, exactly one of them is true, here and here. So this will be true, otherwise it will be false. So both of these will be true. Here we have a true, but both of them are true. So in this case, it will be false and false. Okay, now this is another example that there are two propositions. The first one is election is decided, and the other one is the votes have been counted. Now, this proposition is being denoted by P, and this is being denoted by Q. Now, we have to express each of these compound propositions as an English sentence. Negation of P. So, the statement P is election is decided. Negation will be applying a not. So, negation denotes not. So over here, negation of P will be the election is not decided. Another example, P and this is disjunction. So this is or. Now you have to take both the statements and join them with an or. So the election is decided, or the votes have been counted. Generally, whenever we are creating such type of statements, they don't really make sense in English. So you don't have to make some sort of meaning in English. The statements are not supposed to give some sort of meaning in English. You just have to follow the rules of the logical propositional logic. Next, the next example is given as negation of P and Q. So negation of P we have already done is the election is not decided, and is our conjunction which denotes and. So over here the election is not decided and the votes have been counted. After that, the last statement is implication. So implication is over here we have Q first. So if Q, then P. So this will be written as if the votes have been counted, then the election is decided. Next example. So in the next examples, the propositions have been given, but instead of the propositions that were given earlier, we have been given sentences and we are supposed to write the propositions for the following. So the propositions are the following. It is below freezing, it is snowing, which are P and Q. Now, the first example is it is below freezing and snowing. So if you check which one is the connective, it is and. We know it is a conjunction, so P and Q. Now, it is below freezing but not snowing. I did mention in the earlier class that but is a special case of and. So but and are similar and they both denote and. And we also have a not here. So not is for the snowing, so this will become negation Q. So P and negation Q. Now, the next one is not below freezing, not snowing. So not below freezing is negation P and not snowing negation Q. Now over here this is a bit tricky. It is either or. So I did mention in the earlier class that either or is XOR, correct? But in brackets it is given that it may be snowing or below freezing or both. Now this is a case of here or, not XOR. So this is not XOR, it is or. Why? Because if it is snowing, either snowing or freezing, only just the first part of the statement is given, then it would have been XOR. But since this is mentioned, it will be or. Okay, so if both of them are true, then true. This both denotes this part. So it is the simple disjunction. Now, the next one is if it is below freezing, it is also snowing. Now, if you want to identify this one is very simple that it will be P implies Q if false. If P, then it is also freezing. So this is P implies Q. Let's look at the next example. So the next example, we have been given prepositions. We are supposed to write them in English sentences, but we have over here 3 prepositions. For that, let's begin. The first one is P implies Q. P implies Q can be written as if P then Q. So over here, P is you have the flu. So if you have the flu, then you miss the final exam. Next one, negation of Q by implication R. So by implication means that you have to convert this statement to not. You don't miss the final examination, correct? So, and by implication, if you remember, is if and only if. So for this, it can be written as if you don't miss the final examination, you don't miss the final examination if and only if you pass the course. Or there is another way to write by implication, because in normal English we don't use if and only if. So it is usually written as if you don't miss the final examination, final exam, I'm just shortening it, you will pass the course. And you will pass the course if you don't miss the final exam. Okay, now you might wonder why we have written this statement in this way. So normally if and only if means that both the scenarios, so the first, if we are taking two sentences, then both of them should be valid for each other. So if you are saying that, uh, for example, let's take another example for if and only if. You can take the flight. Let me just write it over here so that I can explain it. P is you can take the flight, and Q is you buy a ticket. Okay, now, so this statement, for this statement P by implication Q will be you can take the flight if and only if you buy a ticket. Okay, or it can also be you can take the flight if you buy a ticket, and if you buy a ticket you can take the flight. So both the scenarios should be written for making it simpler in English, because if and only if is not a term that is used in regular English. Okay, so let's continue with the next one. Q implies negation R. So negation R means R is you pass the course, so negation R will be you don't pass the course, and it will be similar to the first one, if P then Q. So here it will be if Q then not R. So let's just write it. If you miss the final exam, then you will not pass the course. The next one is P or Q or R. So for this, we can write it as you just have to add an or after each statement. So you have the flu, or you miss the final examination, or you pass the course. Okay, so I'll just write it over here. You have the flu, or you miss the final examination, or you pass the course. Okay. Let's continue. So over here we have write the converse, inverse and contrapositive of the following statement. The statement is if today is Sunday, then it is a holiday. So if you remember, if the conditional is P implies Q, then the converse will be Q implies P, inverse will be negation P implies negation Q, and contrapositive will be negation Q implies negation P. Now we have to identify what is P and what is Q. So it is in the form of if P then Q, correct? So today is Sunday is our P. It is a holiday is our Q. Now, so this is P implies Q. Q implies P. So converse will be if today is a holiday, then today is a Sunday. You can write any kind of English. The statement should have the meaning of Q implies P. So if it is a holiday, then today is Sunday. Similarly, inverse, for the statement if today is Sunday, we are adding a not, and then it is not a holiday. And for contrapositive, if today is not a holiday, then today is not Sunday. So not, and then again not. Okay. Now the next topic is precedence of logical operators. For the precedence of logical operators, you have to understand that every time we are finding the truth values for a proposition, we generally construct compound proposition using both negation operators and the logical operators. So if you remember, I've already mentioned that the negation operator is unary operator. Okay, and the logical operators are binary, that is, at minimum they require two propositions. And generally what is done is we use parentheses. So as I've mentioned over here, we use brackets to specify the order in which logical operators are to be used. Now if you have a lot of logical operators in a compound proposition, then you will have a lot of parentheses also. So to reduce the number of parentheses, so we have to reduce the number of parentheses. In that case, precedence or giving priority to the logical operators is important. So in this case, the rules in precedence is that the negation operator is applied before all other operators. So negation operator has the highest priority, which is 1. So this is the highest priority. Okay. And another general rule is that conjunction will be applied before disjunction. So conjunction takes the second priority. This is conjunction or conjunction or and it takes higher priority over disjunction, that is or. And the next, also conditional or implication has a higher priority over biconditional or by implication. Okay, so this is the precedence of logical operator whenever parentheses are not specified, such as in these cases. Here we have negation P and Q. Now negation P and Q means negation should be applied first and then we have to use and. Okay, after that P and Q or R. P and Q, so we have to solve this part first. I'll just write this and then the entire thing second. Over here also this is done first and this entire thing is done second. Next, Q and R will be solved first and then the entire thing, entire proposition. Okay, now translating English sentences. To translate English sentences into propositional logic, it is actually a bit confusing, that is, it is ambiguous. And translating sentences into compound statements removes the confusion. Okay, now the example is this: you can not ride the roller coaster if you are under 4 feet tall unless you are older than 16 years old. Now we have to first identify what are the connectives in this statement. So we have the connectives if, and we also have a not, and we have an unless. Okay, now the next thing is we have to define propositions. The entire statement cannot be taken as one single proposition, so we have to identify the statement in such a way that we have to identify and try to divide the statement in such a way that each part of the statement is a fact which can either be true or false. So now over here you can say that P is you can ride the roller coaster. So negation P will become cannot. You can ride the roller coaster. So I'm just writing RC. Then Q is you are under 4 feet tall and R is you are older than 16. Okay, now for the statement, for the last statement, that is you are older than 16, the simple way is to understand the statement is that if you are not older than 16-year-old, then you cannot ride it. Okay, so you cannot ride the roller coaster if you are not older than 16. So in this way we can see that also this is of the form Q. If we take this part of the statement as Q, so okay, so that is P, and this part is R Q, and you are older than 16 years old is R. Now the next thing, for us we have to identify that our P is negation. So this will become negation P. Okay. And similarly, S is unless you are older than 16 years old. So if you are younger than 16, you cannot ride the roller coaster, correct? So since we are dealing with negation P, our R will also become negation R. Okay. Now there is an F. So this is of the form if Q then P. Okay. So this is of the form if Q then P. But where is our F? It is not at the first position. It is at in the middle. So this is can be written as Q if P. Okay. So this condition should be true for P to happen. So if you are lesser than 16 and if you are under 4 feet tall, then you cannot ride the roller coaster. And also you have to remember that both of these conditions should be true together. Okay, if you are under 4 feet tall and you are lesser than 16, then you cannot ride the roller coaster. So if you notice, this entire thing including 4 feet tall and 16 years old is R, Q and S. Okay, why we are using and? Because both of the conditions should be true if you want to ride the roller coaster. And to riding the roller coaster we have used an F, so Q and negation S implies negation P. Okay, so this is the solution. Now let me just clear the slide so that I can give you the official solution. Yeah. Now one thing to be noticed over here is I used the propositional variables P, Q, R. Here the propositional variables are Q, R and S. Okay. So you can use any kind of propositional variables, but if you match the answer, it will be the same thing. Okay. So if I use this as P, Q, R, then my solution was Q and negation R implies negation P. Okay. Now the next example is how can this English sentence be translated into a logical expression? For this, the statement is you can access the internet from campus only if you are a computer science major or you are not a freshman. So first we have to do the same thing, that is create our simplest propositions. P is you can access the internet. Q will be you are a computer science major. And R is you are not a freshman. Now for this statement to be converted into a logical expression, this is very simple. Here we have an if, okay, only if you have, and you can access the internet from campus only if you are a computer science major or you are not a freshman. So this part can be done easily since we have an or and a not. So we have Q or negation of R, and this is P implies. P implies Q or negation R. Let's look at the solution. Yeah. So here the same thing has happened, that the variables are different. We have used A, C and F, and you can access the internet as A. So A implies C or negation F. Okay. Now the next thing. logic and bit operations. So computers usually use binary numbers, and binary numbers are composed of bits. And bit is basically has two values which can be 0 or 1. Now normally whenever we are saying 1 it means true, and whenever we say 0 it means false. So by convention 1 is true and 0 is false. Now, a variable is called a Boolean variable if its value is either true or false. So, you have a data type also, Boolean data type, where you have the data type's value as either true or false. So, similarly, here we have something known as Boolean variable. Now, there are bit operations that can be applied, and what the operation is that when we are using AND or XOR, we replace our true by 1, okay, and false by 0, the ones I have mentioned here, in logical operations, okay. So every time we were using the truth table, we used to write true true, false false. So the same thing, 1 1 0 0, then true false, true false, 1 0 1 0. Now here doing an OR. So the condition for OR is if both of them are false, it will be false. All the rest are true. The condition for AND, if both of them are true, then only true. All the rest of them are false. The condition for exclusive OR is exactly one of them should be true. So over here, exactly one of them are true, then it will be true, otherwise it is false. So you can just remember it the same way as you remember here AND or XOR in the case of logical operators in propositional logic. Okay, it is very simple. Next, what do you mean by a bit string? So a bit string is a sequence of 0 or more bits. So string, if you remember, it is a sequence of characters. Since it is supposed to be a bit string, it will have bits. So bits are either 0 or 1. So a string made up of 0 or 1s is a bit string. And the length of the string is the number of bits in the string. Okay. Now we have to find the bitwise OR, bitwise AND, and bitwise XOR of the string. So for bitwise OR, let's take this number. I'll explain the first one. Bitwise OR 1 1 0 0 1, and then so over here we have 0 1 and then 1 1 0 1. Now for bitwise OR, that is we are doing OR whenever both of them are false, then only false. So you have to again remember 1 is true, 0 is false, and if both of them are 0, then it will be 0, otherwise it will be 1. So 0 1 will give us a 1, 1 0 will also give us a 1, 1 1 is 1, 0 1 1, then again 1 1 is 1, 1 0 is 1. Okay, so we are seeing it this way. Then 0 0 will give us a 0, then 1 1 1. Okay. Similarly, for bitwise AND, the condition will be if both of them are 1, then only 1, otherwise zeros. And XOR, one of them should be 1 exactly. So let's see the solution. Let's match our solution. So this is 1 1 1 0 1 1, and then again 4 ones. Okay. AND or and XOR can be done by using the truth table in the earlier slide. You can use this table and perform the operations. Now, the next topic is propositional equivalences. So, we first have to understand three terms for propositional equivalences. When a compound proposition is always true, no matter what the truth value of the proposition that occurs in, then it is called a tautology. So whenever the value is always true, then it is called a tautology. So whenever our column, the last column of our proposition is always all the values are true, then it is a tautology. Similarly, if it is always false, it will be a contradiction. So just let me write it over here simply. If all truths, then it is tautology. If all false, then it is a contradiction. And a proposition that is neither a tautology or a contradiction. So a proposition which is neither true nor false, it is known as a contingency. Okay, so these two are important. Contingency is not usually used. So tautology and contradiction is all truths and all false respectively. Now example, if we have p, since we have a single variable, we will have only 2 power 1, which is 2 rows. So we have 2 rows over here, and the two scenarios of p will be, it can either be true or false. Now negation p, we are taking as the not of p, so false and true. Now if we do p or negation p, when you are doing or, one of them should be true. So here this is true and here this is true, so it will both be trues. When you are doing an and, both of them should be true. Since both of them are not true at the same time, this is false. So over here, this column is a tautology and this column is a contradiction. So this entire thing is tautology. And when you get all false in this way, it will be known as a contradiction. Now, logical equivalences. The compound propositions P and Q are logically equivalent if P by implication Q is a tautology. And the notation is P is logically equivalent to Q. So this is the notation for logically equivalent. So in simple terms, so if you have two compound propositions, suppose we have P implies Q and we have negation P or Q. For this, if both of them have the same truth values, then they can be given as logically equivalent. Now let's look at the examples. Compound propositions that have the same truth values in all cases. All possible cases are called logically equivalent. So this is the example, the same compound propositions that I have taken over here. Let's see the truth table. So over here, we have PQ. Negation P will be the not of P, so false, false, true, true. Then negation P or Q. So negation P or Q means we have to solve for these two columns, and the rule is that if both of them are false, it will be false. So over here, both of them are false, so it is false, otherwise all true. And P implies Q is something we have already studied, that if one is true, the other is false, then it will be false. In all the other cases, it will be true. So P implies Q, if one is true, the other is false, it will be false. Now if you look at both the truth values, both of them are exactly the same. They are exactly the same. So in the first row we have true, in the second row false, third true, and fourth true. That means negation P or Q is logically equivalent to P implies Q. And the rule that I've been saying by now, if you have n propositional variables, then we require 2 power n rows. Okay. The same way you can solve for 3 variables. So we have over here three variables P, Q, R, and if you have three variables, you will have 2Q, 8 rows. So we have 8 rows, and the logical equivalence for these two compound propositions are shown. This I'll explain it to you further, but you can just look at the truth table. So for P or Q and R, this is the column, and this one, this is the column. Look at the truth values. The first 5 are true, and the next 3 are false. Here we have it the same way, so we have to compare these two columns. Okay. Now, logical equivalences. We have a few set of logical equivalences that have already been proved, and let's see the following. So these are actually the laws of propositional logic. So the first one we have to see is identity law. So identity law is whenever we have P and T, it is equivalent to P. So now what do you mean by T? So we have P, T, and then we have P and T. So for this, P can be true or false. Now what do you mean by this T? T means the statement is always true. Okay. Now whenever you are doing and, what is the statement if both of them are true? Then only true, otherwise false. Now look over here. These two are similar, right? So this means that P and T is equivalent to P. Similarly, we can do for P, F. So F by F, you can understand easily that F means both of them are false. True, false. And this can be written as P or F. It is giving us true, false will give us, in the case of or, it will give us true, and if both of them are false, it will give us a false. So compare these two columns, we have got the same value as P. Now if you try to connect it, you can say that it is similar to the identity laws in maths. Okay, so this is 1 plus 0 is equal to 1. Okay, so this is similar to our identity laws in maths, and 1 into 1 is equal to 1. So over here the 0 denotes false, plus denotes are or, and denotes multiplication denotes and 1 is denoted by 2. P value can be anything. It can be 1, 2, 3. So these are P values. Okay. So this is similar to our identity laws in maths. Okay. Now the next law is domination laws. Domination law is P, T, P or T. So P is true, false, true, true. Now you have to OR it. So once you OR it, you will get true and true. Both of them are similar, which means this is equivalent to true, which is the same thing given over here. Okay. Similarly, you can prove the other one. Moving on, idempotent laws. Idempotent laws is P, P, P or P. So over here, true, false, true, false. Okay. Now if you OR it, both of them are true, true, and then false. It is the same thing. Okay. So this is similar, that whenever both of them have the same, when you have two propositions the same way, when you AND it or it, you will get the same proposition. Next, negation laws. Now negation laws are important and very useful when you are solving problems on logical equivalences. So negation law is P, negation P. We have to find P or negation P. Similarly, I'll just try to find it and also over here, P and negation P. So this will be true, false, negation P is false true. Whenever we OR it, it will be true false and false true, so both truths. And when you're ANDing it, we don't have two truths at the same time, so we'll just write false. So if you notice, this is equivalent to all truths. So this is a tautology actually, and this is a contradiction. It was one of the examples. Now the next one is double negation law. So double negation law is that you are applying double negation to P. So we have P over here, once negation, then double negation. So P is true false, negation of P will be false true, negation of P will be true false. So this is similar to our P, logically equivalent to our P. Okay, next. The next set of laws are De Morgan's law. De Morgan's law is very important. It is a very important law and is to be remembered very carefully. So before I write the truth table, I'd like to explain the De Morgan's law in this way. So we have P and Q. Okay, whenever we apply complete negation to P and Q, it will be equivalent to applying negation to P, then applying negation to the symbol, and then applying negation to Q. So it is equivalent to negation P. Whenever you apply negation to and, okay, whenever you apply negation to and, so if you're applying negation to and, it will be equivalent to or. Okay, so it will result in or. And whenever you're applying negation to or, it will become and. Okay, so negation of P, so negation is being applied to and, so it will become or. Negation is applied to Q, negation Q. Similarly, negation of P or Q, so whenever we apply negation to the disjunction, this will become the same way negation P. So over here the difference is that you have, instead of and, you have or over here, so negation P and negation Q. Okay, I'll try to prove one of them. So PQ, and then we also need negation P, negation Q. We have to find P and Q, then negation of P and Q, negation P or negation Q. So let's just fill it quickly. Also, one more thing is that if you keep practicing the truth tables, you will be perfect in it. So try to practice it along with the class. Negation P will be false, true, false, true. Now we have to perform AND on these two columns. So AND will be true and then all false, because AND is when both of them are true, then true. Now we have to apply negation to this column, so this will become. After that, we have to perform OR on these two columns. So for that, it will be false because both of them are false. The rest all will be true. Okay. The next is commutative laws. So for commutative laws, this is similar to the mathematics law of a plus b is equal to b plus a, and a into b is equal to b into a. So let's just prove it quickly. P, Q, then you have P or Q, Q or P, P and Q, Q and P. Okay, so for that, here we are doing it in the same way, P or Q. So for or, if one of them is true, then true, and then this one is false. Now look over here that if even if you change the order, it will give us the same truth values. So true, true, false. With P and Q, this will be true, false, false, and then again true, false, false. So if you notice, both of them have the same truth values. Okay, next. Next is absorption law. For absorption law, you have to remember that we have PQ, then you are supposed to find P and Q, and then again I'm just leaving this column P or P and Q. So the same thing. And so true, false, false, and over here we have P or P and Q. So we have to perform or on these two. So to perform or, we have to remember that if one of them is true, then true. So true, true, false, false. This is similar to or equivalent to P. The same way you can prove the other one. The next logical equivalences are associative and distributive laws. The same way I've proved the earlier laws, you can prove the associative and distributive laws too. Thank you.